A single cosmic ray hit a detector in 1991 with the energy of a dropped bowling ball, packed into a particle smaller than an atom. Scientists called it the "oh my god" particle, and that was not even close to the most dangerous form of radiation drifting through space. Cosmic rays like this one are not light. They are particles, stripped nuclei, and protons, blasted across the galaxy at nearly the speed of light. Most of them are harmless by the time they reach you, filtered out by Earth's atmosphere and magnetic field. But strip that shielding away, put a human body in open space, and these particles pass straight through flesh, tearing through DNA, strand by strand. No wall stops them completely. No suit fully blocks them. And the deeper you travel into space, the worse they get. Solar particle events are next, and they come from something much closer to home. Our own sun periodically hurls out storms of protons during violent eruptions on its surface, and those particles can reach near light speed within minutes. A large enough event could deliver a radiation dose in hours that would take years to accumulate on Earth's surface. Astronauts have described these storms as one of the most unpredictable threats in all of spaceflight, because unlike a straightforward hazard you can shield against permanently, a solar storm can spike without warning. But even our sun, brilliant and violent as it is a gentle giant compared to what comes next. Gamma-ray bursts are where things stop being survivable in any traditional sense. A gamma-ray burst is the most energetic form of light in the known universe, released in seconds by the collapse of a massive star, or the collision of dense stellar remnants. In that brief window, it can outshine an entire galaxy. If a burst pointed directly at Earth from a few thousand light-years away, it could strip away a significant portion of the ozone layer in moments. No explosion, no impact, just an invisible beam of light doing damage from across the galaxy. And here is the unsettling part. We would not see it coming. Gamma rays travel at the speed of light itself, so the warning and the event arrive at the exact same instant. That raises an uncomfortable question. What kind of object could produce a beam like that in the first place? The answer takes us to a class of stars unlike anything else in the universe. Magnetars are the next entry, and they redefine what a star can do. A magnetar is the collapsed core of a massive star, crushed down into a sphere roughly 20 kilometers across, holding more mass than our sun. Its magnetic field is so strong that from a distance of 1,000 kilometers, it could theoretically disrupt the chemistry inside a human body, distorting the very molecules that make you who you are. One known magnetar, SGR 1806-20, released more energy in a fraction of a second in 2004 than our sun produces in 100,000 years. Take a stellar corpse, compress it past reason, and you get an object that turns pure magnetism into a planet-scale hazard. But even a magnetar's fury is a localized event. The next form of radiation on this list does not come from one object. It comes from the fabric of the early universe itself. Cosmic microwave background radiation is the oldest light we know of, the afterglow of the universe's birth, filling every corner of space uniformly. On its own, it carries almost no danger, a whisper compared to the other entries here. But it matters because it tells us something disturbing. If the ordinary electromagnetic spectrum ranges from something this faint to something as violent as a gamma-ray burst, then the difference between background noise and total destruction is far smaller than most people assume. If you have made it this far into the electromagnetic spectrum's most extreme corners, drop a like and subscribe, because the next entry does not come from a star at all. It comes from the emptiest, coldest regions of the universe. The next form of radiation is not radiation from something. It is radiation from nothing. Hawking radiation is a theoretical process where black holes slowly leak particles at their edges, a phenomenon that means even the darkest, most crushing objects in existence are not perfectly stable. A black hole with the mass of a mountain, compressed down to the width of a proton, would radiate itself away with the explosive force of millions of nuclear detonations in its final moment. We have never directly observed this radiation, but the mathematics describing it comes from some of the most rigorously tested physics we have. Somewhere in the dark spaces between galaxies, a black hole could be approaching that final moment right now, and we would have no way of knowing until the instant it happened. That thought alone should be unsettling. But the next entry does not wait quietly in the dark. It moves. Rogue neutron stars are next, and they are exactly what they sound like: stellar remnants that have been flung out of their original systems, and now drift through the galaxy with no star, no system, no warning beacon attached to them. A neutron star packs more mass than our Sun into a sphere about 20 kilometers wide, meaning a teaspoon of its material would weigh as much as a mountain. If one passed within a few light years of our solar system, its gravity alone could destabilize the orbits of distant icy bodies at the edge of the solar system, sending them tumbling inward over the following centuries. No light announces its approach because a rogue neutron star can be nearly invisible until it is already close. And if a neutron star can move unseen through the galaxy like that, the next question becomes obvious. What else out there might be moving just as quietly? Rogue black holes answer that question, and the answer is worse. A rogue black hole is a black hole with no visible companion star, drifting silently through interstellar space, betraying its presence only through the way it bends light around it. Estimates suggest our galaxy alone could contain over 100 million black holes of stellar mass, and the vast majority of them have never been detected directly. Picture something with the pulling power to warp the fabric of space itself, sliding through the dark like a shadow with no shape. Astronomers have only confirmed a rogue black hole's presence through gravitational lensing, watching light bend around something that emits nothing on its own. But drifting invisibly is one thing. The next entry does not just hide, it erases. Tidal disruption events happen when a star wanders too close to a supermassive black hole and gets pulled apart by the difference in gravity between its near and far sides, a process called spaghettification. The star's material stretches into a glowing stream before much of it spirals into the black hole, releasing a burst of radiation that can briefly outshine every star and its host galaxy combined. Telescopes have captured dozens of these events across the observable universe, each one a reminder that gravity does not need contact to be lethal. It only needs proximity and enough time. And if a single star can be undone this completely, what happens when the object doing the undoing is not just massive, but active, still feeding, still growing? Quasars are the answer, and they are almost incomprehensibly extreme. A quasar is the blazing core of a young active galaxy powered by a supermassive black hole devouring matter at an enormous rate. The brightest quasars can outshine an entire galaxy of hundreds of billions of stars combined, using a region of space not much larger than our solar system. TON 618, one of the most massive black holes ever identified, holds an estimated 66 billion times the mass of our Sun, an object so large it could swallow our entire solar system out to Pluto without noticing. Take a black hole, feed it billions of years of infalling matter, and you get an engine capable of outshining galaxies. But even a quasar eventually fades as its fuel runs out. The next entry does not fade. It builds, silently, for the entire history of the universe. Vacuum decay is the most theoretical and most absolute entry on this list. Some physicists believe the universe currently exists in a false vacuum, a stable seeming state that may not be the lowest possible energy state reality can occupy. If a small region ever tipped into a lower true vacuum state, the laws of physics within that bubble would change instantly, and the bubble would expand outward at the speed of light in every direction. There would be no warning, because nothing can travel faster than the wall of the event itself. No light would arrive before it. No signal. No chance to react. This remains a mathematical possibility discussed within theoretical physics, not a confirmed threat, but it represents the outer edge of how completely the rules of existence could change without notice. We have covered particles that shred DNA, storms that erase atmospheres in an instant, stars that distort matter itself, objects that vanish into their own destruction, and a threat built into the structure of reality that could rewrite the universe without a sound. Each one exists on a different scale, but together they describe the same truth, that the universe is far stranger and far less forgiving than it first appears from the ground. If you want to keep exploring the physics hiding at the edges of what we understand, subscribe and check the next video in this series, because the universe still has more waiting in the dark.